In this video, we're going to discuss calorimetry and how it pertains to delta H. So first of all, what is calorimetry? So calorimetry is what you basically do upon experimentation. So let's say we were conducting an experiment here, and we were going to dissolve 2 grams of calcium chloride in 50 milliliters of water. So this is our reaction that is taking place. Now, when you set up calorimetry, you use a styrofoam cup. Sometimes you can double insulate this by using 2 styrofoam cups and basically a thermometer. That's basically all the equipment you need in order to perform this lab, besides, of course, a balance to be able to take some masses. So, I'm working with a coffee cup calorimeter here, and the equation that I use for calorimetry is Q equals MC delta T. So let's understand what each of those things mean. Q stands for heat, and we will learn in just a minute what the units for heat will be. This M right here stands for mass of the system. So we'll discuss what the system is. It's whatever you are referring to. It's whatever you are basically analyzing as your system. So we'll get more detailed with that when we get to our experiment. When we take a mass, that mass is measured in grams. C stands for specific heat. Specific heat is related to, or I should say what it's defined as, is how much energy it takes for 1 gram of a substance to raise 1 degree Celsius in temperature. So that's the definition of specific heat. Here's the conceptual component of specific heat. If I have things that are low specific heats, what that means is that if I put energy into it, that temperature can change very drastically. For instance, metals have specific heats. If I put a metal pan on a stove and I turn the stove on, then that metal is going to heat up very quickly. If I take the metal pan off the stove and I let it cool off on the counter or something like that, then it will change temperature. It will decrease in temperature very quickly as well. Okay? Now, if I have water on the other hand, water has a very high specific heat value. So if I put a pan of water on the stove with the same amount of heat, that water might not heat up as quickly as the metal. So the higher specific heat, the lower your temperature changes given the same amount of heat being put in. So that's the conceptual component of specific heat. What we measure specific heat in is joules per grams degrees Celsius. So we actually do leave our temperature in degrees Celsius here. Then we have our last component of the equation, delta T. Delta means final minus initial temperature. So final minus initial temperature. So you'll be taking 2 different measurements, one for initial temperature, one for final temperature, in order to calculate delta T. When we find these temperatures, we need to keep them in degrees Celsius so we can make sure that these units cross out. So let's talk about heat, Q, and its units again. If I am working through this equation and I write down all of my units like I'm supposed to, you'll see that your degrees Celsius cancels out and your grams cancels out as well. So what we're left with is joules. So heat, when we do Q equals MC delta T, that unit that we end up with is joules. We'll talk about the correlation with joules, the heat, and enthalpy in just a minute. But let's look at this experiment and let's kind of work through an example problem dealing with that. So what I have going on here is I have 50 milliliters of water. So I'm measuring out 50 milliliters of water, and I've measured out 2 grams of calcium chloride. And I want to combine them both in this cup. Well, first of all, I'm going to take this 50 milliliters of water and go ahead and pour that into my cup and figure out my initial temperature. So this initial temperature, let's just say we take the reading from my thermometer there, and it's at 22 degrees Celsius. Now, I'm also going to measure out 2 grams of calcium chloride. Now, when I combine these two masses into my cup, that is the mass of my system. So it's the mass of this water plus the mass of the 2 grams of calcium chloride. That is my system, the water and the calcium chloride reacting. Now, the question is, well, 50 milliliters, I thought that was a volume. How do I figure out the mass of water? Well, just because density of water is 1, what that means is that if I have 50 milliliters of water, that's also 50 grams of water, just because the density of water is 1. So, since I have 50 milliliters that I'm putting in the cup, that's 50 grams, plus the 2 grams coming from the calcium chloride. So our mass of our system is 52 grams. Now, let's say I add this 2 grams of calcium chloride into my cup as well. Now, what's going to happen is my temperature is either going to increase or my temperature is going to decrease. If my temperature increases, what that is telling me is that my reaction is releasing energy. And if my reaction is releasing energy, then that means that the reaction is exothermic. If my temperature decreases, what that tells me is that my reaction is absorbing energy from the surroundings and therefore leaving the surroundings to be a lower temperature. If my reaction is absorbing energy, that means that my reaction is endothermic. So sign conventions for Q is the same as sign conventions for delta H. If I have an exothermic reaction, it's a negative Q and a negative delta H value. If I have a reaction that is endothermic, it's a positive Q value and a positive delta H value. So let's say we put our calcium chloride in here with our 50 milliliters of water, and what we actually see is that our temperature increases, okay? So our temperature increases. What we're going to do is read that final temperature that it increased to. So let's just say that it's increasing to 27 degrees Celsius. This is just our fake little experiment here. So our temperature has increased to 27 degrees Celsius. Now what we're going to do is we are going to solve for my heat using this information. Now, the specific heat that we use, that's the only thing that we have that we don't have in our reaction here. The specific heat we're going to use is that of water, which is 4.18 joules per gram degrees Celsius. You don't have to memorize that. I'm pretty sure they will always give you that value if you need to use it for a problem. Whenever you're dissolving something in water, then that is definitely going to be the specific heat that you use. The reason why is because the specific heat of water is so much greater than the specific heat of other things. So what I'm going to do here is solve for Q. Now the Q that I'm solving for is for my surroundings, because I am measuring the temperature of the surroundings. So I plug in the mass, which is 52. I plug in my specific heat, which is 4.18 joules per gram degrees Celsius. And then I'm going to plug in my change in temperature. So my change in temperature is 27 minus 22 degrees Celsius. So that is 5 degrees Celsius there. When I work through this calculation, I end up seeing that my grams cancels out, my degrees Celsius ends up canceling out as well. So I'm left with just joules. So working out that problem, I get Q of the surroundings, I'm going to put SUR, is equal to 1,086.8 joules. So that's 0.8 joules. Now, we aren't looking for the surroundings, we're looking for the reaction here. We're looking for the system that we're looking at. Because our surroundings gained energy, And because we know that it gained energy because it is increasing in temperature, what that means is that the reaction, the system, actually lost energy. And we know that because of the conservation of energy. However much energy was gained by the surroundings was released by the system. Now, sign conventions are extremely important. They're equal in sign. If I absorbed energy, it's positive. If I released energy, then it is a negative value. So negative 1086.8 joules was released from the system to the surroundings from this reaction. Now, how does this correlate to delta H? Well, the difference between delta H and Q is this. Delta H is measured in kilojoules per mole reaction. So there's a couple of things we have to do here in order to convert it to these units. First of all, we have joules. So we have to figure out how many kilojoules that is. And to do that, we're just going to divide by 1,000. So this divided by 1,000 is equal to negative 1.087, essentially, kilojoules. Now, the other thing that's missing to transfer it to delta H is moles of my reaction. So I have to figure out how many moles of that reaction that I used. Now, the substance that I'm going to use is whatever is limiting, whatever is hindering the energy that's being provided there. So I'm going to take these 2 grams of calcium chloride, and I'm going to convert that to moles. So 2 grams of CaCl2 divided by its molar mass. I'll have to look that up real quick. So I looked on my periodic table to figure out what the mass of my calcium chloride was, and it was 110.98 grams. So if I take 2 grams divided by 110.98, I get 0.018 moles of CaCl2. Now what I'm going to do is I'm going to take this value and plug it in down here. I'm going to divide by the number of moles. So 0.018 moles of CaCl2 in my reaction. My reaction is going to give me delta H. So let me do that calculation there. 1.087, a negative value divided by 0.018 gives me a value of negative 60.4 kilojoules per mole reaction. And that will be my enthalpy, my delta H. So to sum that up, to find Q, we use Q equals MC delta T based upon my measurements here. When I find my measurements, that's the surroundings. So what I do is I set my surroundings and system equal to one another. I just take the opposite sign. The reason why is the conservation of energy. Whatever amount of energy is released from one thing is going to be absorbed by the other. Then I have to transfer my energy into kilojoules by dividing by 1,000. After I find my kilojoules, my heat in kilojoules, to transfer it to delta H is I take that Q value in kilojoules and I divide by the moles that I have in my reaction. And it's the moles that is limiting the energy production. Then that will give me my delta H, my enthalpy. So I hope this is helpful, and I hope it will help you. There's lots of lab-based free response questions that deal with calorimetry.